Right, our first speaker will be Professor Stephanie Midgley. She's going to be talking to us in terms of projections, interpretation of future climate change for the deciduous industry, a project that she's been running for the industry for a number of years. Stephanie is well educated with the right credentials and has since 1992 been focusing on climate change impacts, vulnerability and adaptation since 1992. There we go. So is very well versed in a scientific and applied way to be able to present to you. So Stephanie, I'm not going to take more of your time. I'd like to welcome up. So she's at the Western Cape Department of Agriculture now and has walked a road. So Stephanie, over to you. Let's give a round of applause, everyone.
Right, thank you. Yes. Right.
Just the right button. Just keep slides.
Right. Okay, good afternoon, everybody. All right, I'm going to start with, let me get the slide up. As I was starting to prepare for this presentation, it took me back to my very first presentation to the fruit industry on climate change. And in those days, that was a completely new thing. Many people really didn't have any idea of what it was about. And in May 2000, I stood in I think it was the Endler Hall, and I talked about climate change to the Cape Pomological Association. So now, both you and I have now spilled the secret about, how old I am. But I found these slides. I found the presentation from back in 2000, and I thought I'd just show you the cover slide and the last slide. And yes, what has changed? We've come a long way. We have learned a lot. And I want to just say that I'm so excited that the fruit industry has taken this on board, has funded the research that's necessary, and has prioritized it in more recent years just at such a high level. And it's very, very rewarding to see that. Just looking at the history, why I say it goes back a long time, the physics and chemistry of climate change has actually been known for more than 100 years. But if we look at what happens internationally, the Intergovernmental Panel on Climate Change, the IPCC, was established in 1988 on the basis of what the scientists were saying. And the very first assessment report came out in 1990. That was followed by 5 further rounds of assessment reports. And we are now in 2021-22, and the 6th assessment report has just come out. So the first volume was published in August last year, the 2nd and the 3rd volumes in this year. So the scientists are doing their work, working extremely hard. We know so much now. The science is established. Climate change is happening. It's not something for the future. The evidence is there, and we need to act on it. Desmond Tutu actually said once, 25 years ago, people could be excused for not knowing much or doing much about climate change. Today, we have no excuse. All right, I'm going to pick out a few of the headline statements that have come from the recent IPCC 6th assessment report. And one of the very first ones that is based on, it's a massive summary of what the scientists across the world know about climate change, what the impacts are and what we can do about it. One of the first things they said was that recent changes in the climate are widespread, rapid and intensifying, and unprecedented in thousands of years. That statement has become much stronger since the 5th assessment report. And this is why. So if we first look at, this is a set of slides showing how human influence has warmed the climate at a rate that is unprecedented, and they say at least 2,000 years, if not longer. If we look at the right-hand figure, that is the change in global mean surface temperature. The measured or observed data is the black line going up very strongly. And the models, the simulation that goes with that is the pink area around that. And those models include the human influence on climate change, so the burning of fossil fuels and greenhouse gas accumulation, And then the models are then again run without the human influence, and that gives us the blue line. So it's been very clearly established that human activities are causing this problem. And you can see that we haven't had these kinds of temperature increases in a very long time. The right-hand graph goes back 2,000 years. The left-hand graph goes back longer. And that one shows that if we look at multi-century warm periods, yes, there have been these kinds of warm periods before in global history, but if we look at the same kind of level of warming over long periods, then the last time we saw these kinds of levels was more than 100,000 years ago. And that was the last interglacial period, which was between 100 and 120,000 years ago. So we are now reaching a very dangerous level that has not been seen since human civilization emerged. And not that only, but the mean global surface temperature warming has been 1.1 degrees at this point, relative to 1850 to 1900. But if we separate that into the warming over land, we see that over land it's been 1.6 degrees and over the oceans 0.9 degrees. And that map shows that it's not evenly spread around the globe spatially. The land areas obviously getting warmer at a much higher rate. The more red they are, the higher is the rate of warming. And you can see that, obviously we know about the Arctic, that is really warming at a very, very rapid rate. But even Southern Africa, we have a very dark patch of red there. And basically, the data for Southern Africa shows that our warming is twice the global average at this point. Second headline statement from the IPCC. It's now indisputable that human activities are causing climate change. And by doing so, we are now making extreme climate events, such as heat waves, heavy rainfall, droughts, and so on. We're making them more frequent and more severe. And I want to just say a little bit about extreme events. The scientists, and there's a particular set of scientists that have been working really, really hard in the last 10 years or so to work out methods of finding out whether a particular extreme event can be linked to climate change, or to what degree it can be linked to climate change. And it's called climate change attribution science. And it was even given a prize quite recently, those scientists. So what they're now doing is they're looking at these terrible events all over the globe, and they're doing the sums to find out how many times more probable was that event given the human activities that are causing climate change compared to the natural probability of those events occurring in that particular area. The very top left picture you can see is Tewaterskloof Dam. That was taken in 2018, and that particular drought was 3 times more probable because of human climate change than normal conditions. Then the middle one is the KwaZulu-Natal floods of this year. Those are 2 times more probable. And that is based on the actual rainfall patterns, the way the rain came down. It's not based on lack of infrastructure maintenance or any of those kinds of things that affect impact. Just the hydrological and the meteorological conditions, twice as probable. If we look at the bottom left, that is the heat wave that India and Pakistan have experienced from March to May this year. Exceedingly hot temperatures in Delhi, I think going up to 48, 49 degrees. And that has been found to be 30 times more probable because of climate change. The middle one at the bottom is the German floods of 2021, Germany and Belgium, exacerbated by climate change. They haven't done finalized the studies yet, but certainly also extreme rainfall there. And then the right-hand one is the exceedingly hot temperatures that were experienced in 2021 in the Pacific Northwest of USA and Canada. And of course the wildfires that came with that. And those have been found to be virtually impossible if we don't factor in human climate change. All right, so last statement I'm going to use from the IPCC: unless there are immediate, rapid, and large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees Celsius will be beyond reach. So basically, we are almost at the point where 1.5 will not be achievable. We are heading towards 2 degrees, and in fact, the current policies and pledges from different countries about what they're going to do is taking us to 2.8 degrees. And if you think about what it means that land areas are much warming more rapidly than that, then we're going into the 3 to 4 degrees over land. Right, so we are really in quite a big crisis. How's the world responding? The United Nations Framework Convention on Climate Change has been holding their meetings for, I don't know how many years now, 27 years. They're having these the meetings where they're trying to decide how they're going to deal with it. So the policy response has been there. It's been very, very difficult, and we've come up with all sorts of things like the Kyoto Protocol, the Copenhagen Accord, then the Paris Agreement 2015. So the countries are really trying to grapple with this and come up with policy responses, but the problem continues. And it's a very, very tricky problem. It's very complex. But we can't afford to wait until the costs of damages to economies and to people and to the environment start to exceed the cost of actually investing in the response at this point and solving the problem. All right, I'm going to get now to some of the global science, or the underlying science that is used when we talk about the future, the projections of climate change. What are we expecting over the next 80 years or so? And to do that, I need to first show you these two figures. So this work, and I think it was stated very clearly this morning, when you talk about futures, you can never predict the future. That is a word we never ever use. We can't predict climate change. What we can do is we can use scenarios, and that is what the scientists are doing. Different scenarios of economic development, of the way the development of the use of fossil fuels or the reduction in the use of fossil fuels. And those are the different scenarios that were used for the last assessment report. And you can see there on the left-hand side, there are scenarios that capture high rates of fossil fuel usage, continued or business as usual based on coal and oil. Those are the very top ones, the SSP 5 to 8.5, and that takes us to a very, very high level of warming. And then we have other ones where countries' mitigation actions are to some extent successful, we reduce fossil fuel use. And then the very bottom ones are the ones that we really want to achieve, where we go net zero and we go below net zero. So we actually reverse the problem to some degree. And those are the 5 that are then used to model what we see on the right-hand side, which is the projected change going into the future to the end of the century, according to those different scenarios. Now, the best case scenario, we should be able to stay under 2 degrees warming, the blue one at the bottom, future based on sustainability, and the worst one is future with intensive fossil fuel use, and that takes us up to about 4.5 degrees Celsius global average warming. All right, so it's important that we understand how the science is done, and we understand the scenarios that actually are behind the statements that are made. And we don't have to end up at that 4.5 degrees Celsius scenario. If we do the right things, we could well end up under 2 degrees or even under 1.5 if we acted very quickly now. Right, the other thing I need to explain is that the modelers then use what's called general circulation models. And there are many, many tens of different models that have been developed, so we don't only use one model, and there certainly is never one best model. So what the scientists do is they take 25 models as what they call an ensemble model. So 25 different climate models, and then 5 years later they develop more 25 models. So we look at the means or the range of what those models are telling us, and there isn't one best model because they all have their strengths and weaknesses. Rainfall projections and all the models are still much more difficult than for temperature. I'm not going to go into the details around that. I've highlighted some of them there. But so we need to be much more cautious when we look at the projections for rainfall than we are for temperature. And then we look at timescales. So we need to have a high-quality historical data set that we can work on that gives us the baseline. Then we look at the short term, which is really until the 2030s. In the case of the fruit industry, it makes more sense to look at the middle of the century, the kind of time frames where we're planting orchards for 20, 30 years. And then we have the end of the century timelines as well. So I'm mainly going to show you the mid-century projections in this presentation. And then just very quickly, the projections globally for temperature. And these 3 maps show the world as it will warm if we have a mean global warming of 1.5 degrees Celsius. In the left-hand map, the middle one is 2 degrees, and the right-hand one is 4 degrees. And you'll see that Southern Africa is always a bit redder than many other areas. So if we just look at the 2 degrees global warming, if we achieve that, then warming in South Africa would be between 2.5 and 3 degrees warming over the land area. And the more fossil fuels we burn, the more warming we get, obviously. And then also with every increment of global warming, we get increasing increments of what that means for rainfall. Overall, rainfall is projected to increase in many parts of the world, and the globe as a whole is going to get wetter, warmer and wetter. But there are certain areas, and particularly some of the subtropical areas, and all the Mediterranean areas that are projected by almost all the models to be getting drier. And if we just look at the middle map of 2 degrees Celsius and the 4 degrees Celsius, I've pointed out the brown areas there in Southern Africa. That means that we're expecting decreasing rainfall over those parts. But if you look at Chile, California, the Mediterranean basin, Western Australia, those are all Mediterranean regions with similar agriculture, fruit production, and they're all projected to be getting drier in future. And drought is another symptom of that. As you can see, also those areas expected to be experiencing more frequent and more intense droughts in future. And by the middle of the century, probably about 2.5 times more likelihood of bad droughts compared to the past. All right, and now what are we doing in the Western Cape and what are we doing in the fruit industry? And I'm going to show you a little bit more detail of the science that's been done here, and I'm going to draw mainly on 2 studies. The first one is the one I'm showing in the middle there. It was funded by Hortgro Science, the Scientific and Practical Guide to Climate Change and Poem and Stone Fruit Production in South Africa. That project was completed last year. Many analyses and maps that are available, and industries making those reports available, and will also make the maps available probably in an online form at some point. So that is the one study, and if you look at the map on the left-hand side, that shows the 11 different fruit regions that the modeling was done for, and for some of the, for example, for chill unit accumulation, it was done at national level as well. And then the right-hand side is a report that's just come out, or that we just received this year. It was commissioned by the Western Cape Department of Agriculture, and we got the climatologists at University of Cape Town at the Climate Systems Analysis Group to do the study for us, and it's a complete scientific revision update of the climate science, both the trend analysis and the projections for the future for the Western Cape in very high spatial detail. So 23 different agroclimatic zones across the Western Cape. That report is currently being finalized for public dissemination, and everybody can have a look at that. There are also many, actually hundreds of maps that will be added to the Cape Farm Mapper. So for farmers who want to use Cape Farm Mapper for that purpose, for decision making, that resource will become available. All right, just a handful of slides to pick from some of those, from those studies. So starting with the study from the UCT climatologists, these are the trends, what is already happening until 2020, in fact for a century, 1902 to 2020. And the left-hand set of graphs shows daily minimum temperatures and the trend there. So the more red it is, the higher rate of warming of the minimum temperatures. And you can see that the main area of concern there is up the west coast, including the Bokkerveld, and going up towards Namibia, and mainly in the autumn and the spring season. So the top left is MAM, that's March, April, May, that's autumn. Top right is June, July, August, winter. Bottom left is spring, and bottom right is December. So we can see that the main thing, the way things are happening at the moment in the Western Cape is on minimum temperatures. On maximum temperatures, you can see it's very different. It's more in the inland areas. All right, I'm going to have to go through this quickly now. All right, the trend in rainfall, the one that's of really big concern is the decreasing rainfall in autumn, the top left graph. We're seeing very strong reductions there. Those are all significant. So the hash areas are areas where it's not a significant trend, but we're seeing that very clear drying in autumn. All right, and I'm going to actually flip through this because I think I'm going too slowly. So I'm just going to come to the futures now in terms of mean annual temperature. You can see the trends there for South Africa, less so on the coast and much more so on the inland areas. And then if you look at the right-hand map specifically for the Western Cape, you can see that as well in a different study. What does that mean for chill units? It really means that chill units are decreasing, as one would expect. And these maps show the historical on the left-hand side and the future accumulation of chill units. And the more green there is, the dark greens mean that's a high accumulation of chill units, and you can see those becoming much less in future, being restricted to the very high-lying areas. And this is about 2050. The time that it takes to reach certain thresholds of chill units, 250, 500, or 700 chill units, we can see the right-hand set of graphs showing how that changes compared to the historical side. A huge reduction, especially on the higher chill units of areas that will get those kinds of units in future. High temperature stress, we're also seeing increases mainly more into the inland areas. The right-hand figure shows the dark reds, where there's a very high increase in daytime maximum temperature. All right, and then days conducive to color development in red apples, and we took March and April, and we looked at the days where we know that the conditions are right for color to be initiated and to be developed in the fruit, and we see very many numbers of days of reduction of those days that are conducive, so between 9 and 18 days reduction, more so in some areas, especially the coastal areas of Elgin-Grabo, really being limited to maybe 3 to 9 such days in those 2 months in future. Then mean annual rainfall, we see the drying trend, the brown colors in the graph showing where we think that future will be a drier future, and also Limpopo is another area. But then there are other areas in South Africa where it's not so clear, and in fact, some cases it may be even getting wetter. And the bottom right-hand graph also shows that especially the core winter rainfall area expected to be getting drier, whereas some parts of the summer rainfall area, the central Karoo and so on, possibly getting wetter. These are the timelines of how that drying is expected to pan out. We'll see probably from about the early 2040s, the 2050s, we'll see the clear signal coming through of the drying, where all the models basically say it's getting dry. All right. What does it mean for rainfall? The patterns of rainfall changing very, very dynamically. So long dry spells, but then also heavy rainfall, more convective storms maybe. We don't know too much about, the big question always in the fruit industry is hail. What do we know about future hail risk? We know very little about it actually, so there are areas where we really need to do more work. And then I'm not going to go into the detail of how this figure, what this means, but really it's the risk of drought, moderate drought, 1 in 10 years becoming a 2 in 10 years, a 3, 4, 5, and by the middle of the century, we have 5 or 6 years of that kind of drought given climate change. All right, and then some of the other risks of course, we know about the sunburn risks, we know about decreasing frost, which could be a positive, could also be a negative in some cases, increasing heat units, pests multiplying more quickly, rising evapotranspiration, and we modeled this, it was roughly 100 millimeters per year increase in evapotranspiration, and then possibly increasing wind speeds, and we don't really know too much about hail, as I said just now, but there could be increases in some areas. The summary of impact, so the southwestern production areas probably at greatest risk, and then some of the northwestern high-lying areas, the Bokkerveld and so on, the Langkloof, probably remaining pretty much viable, but just having to deal with those extreme hot days and so on, and then just additional water that needs to be given to the trees to account for rising evapotranspiration. And for stone fruit production, the Klein Karoo, showing that it's a very vulnerable area, some areas possibly becoming marginal, and just looking very, very closely at the kind of cultivars that are used in the stone fruit industry to track what's happening with climate change. All right, this is actually the last slide. I hope you can give me 2 minutes for this one. I think this is really my main message. We heard this morning about the new area we're in, the Anthropocene. It means that where humans are really controlling the globe, what we're doing with the globe. And all of these, what I'm calling these global and local transitions, are happening everywhere in the world, but they're also happening here. And many of them, all of them actually linked to climate change in some way or another. And we have a toolbox of solutions available, and practically all the tools we have in our toolbox for the fruit industry fall under these categories. So we have transitions in terms of land, soil health, water use, genetic transitions, what are we planting, and there are solutions emerging, regenerative agriculture and others, water productivity, just using our resources more carefully. Then we have infrastructure transitions, where we know about the problems with road and rail and ports and so on, but we need those things to function if we want to be adaptive, but climate can also affect those infrastructures. We see that in KwaZulu-Natal, what happened there. Then energy transitions, I'm not going to say too much about that, I think it's obvious, renewable sources coming in so strongly. Then the dietary transitions, which are going to be a big opportunity for the fruit industry. The circular economy, where we make use of waste much more effectively, and that is a whole new area of economic growth and job creation. And then the population transition. People are moving, often as a result of climate change. But all of these things are happening together, and I think that bottom statement from the IPCC, I think, captures it. So climate change impacts and risks are becoming increasingly complex and difficult to manage. They're all interlinked somehow. Multiple climate hazards are occurring simultaneously, and multiple climatic and non-climatic risks will interact, resulting in compounding overall risk, cascading across sectors and regions. It's not something that is just in the environment sector. For a long time, people always said, oh, that's for environment. No, it's going to affect everything, all parts of society and the way we run our economies in this world. My last slide then, I think there is good news. We do understand the causes. There's no question. We understand what's going on. We know why it's happening. And we do actually know by now the pathways of getting ourselves out of this problem. We just have to act on that now. We do have most of the solutions. And what we don't know yet, research and development can give us in the next 5 to 10 years. And it's not too late to do something about it. And the last IPCC report that came out this year on mitigation, what can we do about it, made that very, very clear. And they spelt it out very clearly. These are the things we can do about it. The solutions are there. The technology is often already there. We just need the political will and the financing to do it. Many of these solutions also are opportunities, I think, especially in the fruit industries. There are co-benefits for human well-being, for sustainable development, environmental health, and so on. So not all of these things are just going to be a drain on our resources. They are going to make things better. And if we act now, we have to do so together. We can't do it on our own, and together means partnerships with government, with the industry, farmers, researchers, etc. And we need to have a shared vision of where we're going and what that future must look like. And I think it's really important to say that everything everybody does, every year matters, every action matters, and it all needs to happen together across the world to get to grips with this problem. All right, thank you.